Coming up. Okay, good. I'm going to talk about a particularly interesting technology that has come of age, especially in the context of AI agents. And this is work that I've been working on for decades, but most recently at the Cognizant AI Lab, which is right across the bay. So the motivation is that AI has actually matured from being a tool from imitating what people do to actually creating new things, to making decisions, becoming agents. And the question is then, how can we discover creative decision strategies? It doesn't come from gradient descent. I mean, that's imitation. And even reinforcement learning is really climbing the nearest hill. You have one individual, you try to incrementally improve it and get to the top of that hill. But there's limited amount of creativity that you can establish that way. This is a challenge that creative decision-making has faced. There may be many different strategies, and they be very different, and each one of them good in their own way. How do we find the good ones? The space is really huge, the space is really large dimensional, and it's deceptive. So the solution is population-based search, also known as evolutionary computation. The idea here is that you have a lot of individuals, the whole population, and it's spread out across the solution space. And it's not just a bunch of individual searches, they talk to each other. You have crossover that allows you to recombine two good solutions in order to find something that's even better. For instance, this one crossed over with that one might give you that peak. And surprisingly, this actually works really well. It scales up really well. In high-dimensional spaces, for instance, you can solve problems with 1 billion variables. Remember, humans can handle maybe 7 plus minus 2, Bayesian optimization maybe 10 dimensions. This is 1 billion variables. Kalyan Moidab on metal alloy manufacturing process showed that. Also very large search spaces where there are potentially 2 to the 70th solutions. That's like a multiplexer design problem of 70 bits. Hormuth Sarsad and Babakodjet showed that you can solve this using evolutionary search. Just to get you an idea what that number actually is. 2 to the 70th looks pretty compact. If you write it out as a decimal number, it takes light 95 years to go from the beginning of the number to the end of the number, 10-point font. So that's how many states there are. You can still find solutions because these searches talk. You find a partial solution, another one in this population maybe finds another part of the solution. You recombine them, and this way you can make progress and find solutions in a space that's large. All right, so, and for deceptive spaces, there are techniques that we've been working on in the evolution computation community for decades. So we can find surprising solutions that are also useful. Now, evolving neural networks is a special case of population-based search. There, our population consists of encodings of neural networks. Most likely lists or trees, something simple that then decodes to a neural net that we evaluate in the environment, and that becomes the fitness of each individual. And then we recombine them using crossover and maybe mutate them to find new kinds of DNA. This way we can discover solutions that are complex, creative, and customized to the task. So this is actually a visualization of a neural network that was discovered this way to control a robot in a competitive foraging and pursuit evasion task. So that's neuroevolution, applying evolution optimization to neural networks. Now, let's get to the agent strategies. So in the real world, what we would like to do is evolve a neural network that takes the current problem or the context as input and produces actions, the decision as output. And then we'd like to do it in such a manner that this neural network, this decision strategy, optimizes the outcomes. It might be, for instance, rehabilitation or treatment of a disease or marketing strategy or something like that, a decision strategy. Now, in the real world, it may be dangerous. I mean, you don't want to experiment different decision strategies on people, like what drugs to prescribe for a patient. You want to have a surrogate model of the world. And here we can use standard machine learning. We collected a big data set of decisions in the past. For these situations, this action was performed, this was the outcome. We can train a model, just plain neural network, to imitate that data. That's the imitation. We know how to do that well. Once we have the surrogate, then we can evolve a neural network. Each time we have a candidate, we don't put it in the real world. We ask the surrogate model, how good is this decision strategy? And this way we can quickly evaluate millions of different decision strategies in order to find the good ones. So this is the extension to current AI. We are not just predicting what will happen, which we already know how to do, but we also figure out what we should do about it. That's the new AI. All right, so a couple of examples of that. First, designing websites so that we have optimal number of conversions. You go to this site and you're really compelled to press this button, find my program. That's a conversion. And this is a real-world application. It actually is running in the world. This was designing the widget here, the sign-up widget for this website that advertises educational programs. And it was actually evaluated in the real world while it was searching. And the professionals who designed these websites called this approach the ugly widget generator. Because to them, these widgets look ugly. They did not adhere to design principles, which are, for instance, common colors and all kinds of simple things like that. This is what the humans came up with. It's much more boring. This one is much more on your face and something that converts actually 45% better. So this is what is the running theme of this AI-based evolution and population-based search. It discovers solutions that humans miss, and they perform better. Another example is in cyber agriculture. This was a collaboration with MIT Media Lab, Caleb Harper. They have computer-controlled greenhouses, or they're actually containers where you control how much light goes in, what kind of light, temperature, nutrients, water, everything is computer-controlled, and we don't really know what to do. Farmers know about their land, but not in general what you should do. So we evolved growth recipes. And actually here we're just displaying what kind of light should be shone on basil so that it grows better. And evolution discovered that basil doesn't need to sleep. You can have the lights on 24 hours and it will thrive. It becomes bigger and tastier. A huge surprise to the biologists. They thought that plants need to rest, like every one of us. But it turns out that they actually thrive in 24 hours. We would never have discovered that if evolution hadn't done it. Third example, this is something we built during the pandemic. A prediction model of how the cases will develop over the COVID-19 pandemic with certain restrictions that the government will impose. Should they close the schools, workplaces, stay-at-home requirements, mask, contact tracing, various actions that can be done, how they affect the pandemic. And again, we have a prescriptive, predictive model that allows us to predict based on past history and past restrictions, and then make optimal recommendations. How can we keep the pandemic in check while at the same time economic impact at the minimum? If you're interested, there's an interactive demo where you can explore how things could have happened in the past. And it discovered things that we did not know. It first focused on schools and workplaces, and later predicted and would have mitigated the Delta surge if the government only had listened. But also it came up with creative solutions, like different restrictions on weekdays and weekends, agility, quick changes, and focus on certain dimensions. All right, so how can we trust the solutions? That's a lot of technology that goes into predicting the confidence intervals around the predictions, explaining them with rule sets, and also, even with LLM, we can evaluate how confident we are with the LLM output. Last point, multi-agent coordination. We can build systems, multi-agent systems using these technologies, and they will result in better abilities in terms of flexibility and reliability. And later on, Dan Fink will give a short talk and hopefully also a demo of the system in the 4:30 session. All right, to conclude, decision-making agents are the future of AI. Neuroevolution discovers decision strategies, including creative solutions, useful solutions that you don't already know. And techniques that exist to make them trustworthy. And this, in the long term, should make AI-driven society possible in science, engineering, business, healthcare, other aspects, education, and so on. So there are lots of resources available if you're interested in diving deeper, we have a textbook or actual monograph coming out in a couple of weeks in HTML later at MIT Press in a physical form on neuroevolution. There's also a tutorial which has a video and slides, and much of this software is available open source, including the uncertainty and neuroscience system as well as the decision making. So that's it. Thank you.